welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 1059, all paths from source lead to destination. This problem challenges us to determine if every path starting from a given source node leads to a specific destination node in a directed graph. It's a fascinating problem that tests our understanding of graph traversal and cycle detection. Let's dive in and explore the solution step by step. In this problem, you are given a directed graph with n nodes, labeled from 0 to n1, and a list of directed edges. Each edge is represented as a pair, u, v, indicating a directed edge from node u to node v. The graph is well defined, meaning it doesn't have self-loops or duplicate edges, although it may contain cycles. Your goal is to determine whether all paths starting from a specified source node ultimately lead to a specified destination node. To do this, there are three critical conditions to evaluate. First, the graph should not contain any cycles. Second, every valid path starting from the source must eventually terminate at the destination. And third, the destination node must not have any outgoing edges, meaning it should be a terminal node. These conditions ensure that all paths from the source node lead to the destination node without exceptions. The input includes the number of nodes, the list of edges, the source node, and the destination node, and the output is a Boolean value indicating whether the conditions are met. The output of the problem is simple: return true if all paths starting from the source node lead to the destination node, otherwise return false. Let's look at an example to better understand the requirements. Consider a graph with 4 nodes and the following edges: 0, 1, 0, 2, 1, 3, and 2, 3. The source node is 0, and the destination node is 3. In this case, the output is true. This is because every path starting from node 0 eventually reaches node 3, and node 3 satisfies the conditions of being a terminal node with no outgoing edges. To elaborate, in the given example, there are 2 possible paths starting from the source node 0. The first path is 0-1-3, and the second path is 0-2-3. Both paths terminate at node 3, which is the destination. Node 3 has no outgoing edges, meaning it serves as a terminal node. Furthermore, the graph does not contain any cycles, so the condition that all paths must eventually terminate at the destination is satisfied. Since all 3 conditions are met, the output is true. Now, consider a different example with the same number of nodes but a slightly modified graph. The edges are 0, 1, 0, 2, 1, 3, and 2, 1. The source remains 0, and the destination is still 3. In this case, the output is false. While one path, 0-1-3, does terminate at the destination, another path, 0-2-1-3, introduces a cycle. Specifically, the cycle 1-2-1 violates the condition that every path must terminate at the destination. Since not all paths from the source lead to the destination, the output is false. Lastly, consider another example with 3 nodes and edges, 0, 1, 1, 2, and 2, 1. The source is node 0, and the destination is node 2. Here, the output is false for 2 reasons. First, the graph contains a cycle, 1-2-1, which violates the requirement that all paths must terminate at the destination. Second, the destination node 2 has an outgoing edge, 2-1, meaning it is not a terminal node. These violations make it impossible for all paths to satisfy the given conditions. The constraints for this problem ensure that the graph is directed and free of self-loops or duplicate edges, but it may contain cycles. Some edge cases to consider include graphs with no outgoing edges from the source, graphs where the destination node has outgoing edges, or graphs with multiple paths and cycles. These scenarios highlight the need for a careful evaluation of the given conditions. To solve the problem of determining whether all paths from the source node lead to the destination node in a directed graph, we need to consider a few important challenges. Since the graph can contain cycles, we must carefully handle infinite loops and dead ends. The first approach we could take is a brute force depth first search, or DFS, with explicit path tracking. Here, we explore all possible paths starting from the source node. For every path, we check 2 things: if it ends at the destination node, or if it ends at a dead-end node that is not the destination. A key issue with this approach is handling cycles. If a cycle is encountered, we must ensure it doesn't lead to an infinite loop. Additionally, if even one path terminates at a node other than the destination, the result must be false. While this method is conceptually simple, it's computationally expensive. The time complexity is O, V plus E, in connected graphs, but redundant path tracking can lead to exponential time if cycles are not pruned. This makes the brute force method inefficient, especially for large or cyclic graphs, and requires additional logic to handle cycles explicitly. To overcome the inefficiencies of the brute force approach, we can employ an optimized DFS with both cycle detection and memoization. This method significantly improves efficiency by avoiding redundant computations and addressing cycles early. The process involves using a visited set to detect cycles and a state array to memoize results for each node. A node's result is stored as true if it leads to the destination, and false otherwise. For each node, we check if it has outgoing edges. If it doesn't, the node must either be the destination or the entire path is invalid. The outgoing edges are then explored recursively using DFS. Memoization ensures that once a node's result is determined, it doesn't need to be recomputed, and cycle detection prevents infinite loops. This approach has a time complexity of O, V plus E, as each node and edge is processed only once. While it requires extra space for memoization, it is particularly well suited for sparse graphs, offering a practical trade-off between efficiency and memory usage. Another approach to consider is using an iterative method based on topological sorting. Here, we avoid recursion by processing nodes iteratively, in a manner similar to topological order. Nodes with no outgoing edges are tracked, and results are propagated backward to earlier nodes. This allows us to determine if all paths eventually lead to the destination. An important observation is that nodes processed earlier have a direct impact on the results of nodes processed later. While this approach eliminates the need for recursion, handling cycles and correctly propagating results can be more complex. The time complexity remains O, V plus E, but this method is particularly suitable for acyclic graphs. However, the additional complexity in implementing cycle detection and result propagation makes it less straightforward compared to the optimized DFS approach. Among the approaches considered, the optimized DFS with cycle detection and memoization stands out as the most suitable strategy for this problem. The key insight here is that DFS allows us to explore all paths efficiently, while memoization ensures we avoid redundant computations. Additionally, the use of a visited set for detecting cycles prevents infinite loops, which is crucial for handling cyclic graphs. The realization that these two techniques, cycle detection and memoization, can work together to solve the problem efficiently was the aha moment that led to this choice. This method strikes the right balance between simplicity and efficiency. It effectively handles cyclic graphs, avoids the exponential time complexity of naive DFS, and ensures correctness. While it does require slightly more memory due to memoization, this trade-off is justified by the significant gains in efficiency and clarity. Overall, this approach provides the most reliable and scalable solution for determining if all paths lead to the destination. In this problem, we're tasked with determining whether every path starting from a given source node in a directed graph ends at a specific destination node. The graph may have cycles, which we must account for, and we need to ensure that all paths terminate correctly without getting stuck in loops or diverging to dead ends. If any path fails to meet these criteria, the answer should be false. To solve this, we'll use a depth-first search, or DFS, approach with cycle detection and memoization. First, we represent the graph using an adjacency list, where each node maps to a list of its neighbors. This representation is both space-efficient and allows for quick traversal of neighbors during our DFS. For example, given edges like 0, 1, 0, 2, 1, 2, 2, 3, the adjacency list would look like 0, 1, 2, 1, 2, 2, 3, 3. This structure is key to efficiently navigating the graph as we explore paths from the source node. Next, we define some critical base cases to handle edge situations in the graph. If the source node has no outgoing edges but isn't the destination, it's considered a dead end, and we return false. Similarly, if the destination node has outgoing edges, it's invalid, as paths shouldn't continue beyond the destination. Additionally, if we detect a cycle during traversal, the output must be false, as cycles create infinite loops. To implement our DFS, we use a visited set for cycle detection and a memoization dictionary to store results of subproblems. This avoids redundant computation by reusing results for nodes we've already processed. The recursive DFS function operates on the current node, checking for cycles by determining if the node is already in the visited set. If the result for the node is stored in memo, it's returned immediately. If the node has no outgoing edges, we verify whether it matches the destination. Otherwise, we recursively explore all neighbors, ensuring each leads to the destination. If any neighbor fails, we return false. Once all checks pass, the node is removed from the visited set and its result is stored in memo for future use. To complete the solution, we call the DFS function starting from the source node. If it returns true, we know that all paths from the source lead to the destination. If not, we return false. Some key insights make this approach effective. First, cycle detection through the visited set ensures that we don't get stuck in infinite loops during our traversal. Memoization allows us to optimize performance by storing results for nodes that have already been evaluated, reducing the overall time complexity. Additionally, defining robust base cases ensures that we handle edge cases like dead ends or invalid destination nodes correctly. The primary data structures used here include the adjacency list for graph representation, the visited set for cycle detection, and the memo dictionary for dynamic programming. Together, these create a systematic and efficient way to determine if all paths meet the problem's criteria. Analyzing the algorithm's complexity, the time complexity is O, V plus E, where V is the number of nodes and E is the number of edges. This is because each node and edge is processed at most once during the DFS traversal. The space complexity is O, V, which comes from the visited set, the memo dictionary, and the recursion stack. It's critical to consider edge cases when applying this solution. For instance, in a disconnected graph, we ensure that only paths originating from the source node are considered. Cycles, including self-loops, are handled by the visited set, preventing infinite loops. Dead ends, where a path terminates at a node other than the destination, are explicitly checked in our base cases. These considerations ensure that the algorithm is robust and handles a wide variety of graph structures correctly. To understand how the algorithm works, let's walk through an example. Suppose we have 4 nodes and edges, 0, 1, 0, 2, 1, 2, 2, 3, with the source as node 0 and the destination as node 3. First, we build the adjacency list, which results in 0, 1, 2, 1, 2, 2, 3, 3. Starting the DFS from node 0, we explore its neighbors 1 and 2. For neighbor 1, we recursively explore its neighbor 2, which leads to 3, a valid path. For neighbor 2, we directly reach 3, another valid path. Since all paths from the source lead to the destination, the algorithm returns true. This example highlights how the adjacency list, DFS traversal, and memoization work together to verify the problem's requirements efficiently. To solve the problem of determining if all paths from the source lead to the destination, we start by representing the graph using an adjacency list. This is done with the help of Python's default dict, which allows us to conveniently append neighbors for each node. Once the graph is built from the given edges, we perform a quick validation check. If the destination node has any outgoing edges, we can immediately return false, since a valid destination must not lead anywhere else. Next, we define an array state to track the visitation status of each node during our depth-first search. Here, we use 3 states, 0 for unvisited, 1 for visiting, and 2 for visited. The DFS function is then defined to explore the graph. If a node is encountered that is already in the visiting state, it indicates a cycle, and we return false. Similarly, if the node is already fully processed, we can skip it by returning true. At this point, we mark the current node as visiting and check whether it is a leaf node. If it is a leaf but not the destination, we return false, as all paths must terminate at the destination. If the current node is not a leaf, we proceed to recursively visit all its neighbors. For each neighbor, we call the DFS function. If any recursive call returns false, it indicates that the path does not satisfy the problem constraints, and we return false as well. Once all neighbors have been successfully explored, we mark the current node as fully visited by setting its state to 2. This ensures that it will not be revisited unnecessarily in subsequent calls. Finally, the function returns true, signaling that this node and its paths meet the required conditions. The depth-first search is initiated from the source node, and the result of the DFS function determines whether all paths from the source indeed lead to the destination. This approach ensures that we not only handle cycles and dead ends but also validate that the destination is the only valid endpoint for all paths. Here, we begin the Java implementation of the solution. The first step is to build the graph using an adjacency list. This is achieved with a hash map, where each node is a key, and its value is a list of neighboring nodes. We iterate over the edges array and populate the graph with this mapping. Next, we handle a critical edge case. If the destination node has outgoing edges, we immediately return false, because all paths leading to the destination would not be valid if it can lead to other nodes. After that, we define an array called state to track the visitation status of each node during our depth-first search. The states are represented as integers, 0 for unvisited, 1 for currently visiting, and 2 for fully processed. Finally, we call the helper method DFS, passing in the source node, destination node, the graph, and the state array. The DFS function will perform the actual traversal and validation of the paths. Within the DFS method, we start by checking if the current node is already being visited, indicated by a state of 1. This would mean a cycle is detected, and we return false in such cases. If the node has already been fully processed, indicated by a state of 2, we simply return true, as the node has been validated. Then, we mark the current node as visiting by setting its state to 1. If the node is a leaf, meaning it has no outgoing edges, we check if it matches the destination. If it doesn't, we return false, otherwise, we mark the node as visited and return true. For nodes with outgoing edges, we recursively call DFS on all their neighbors. If any recursive call returns false, we propagate that result up the recursion stack. Once all neighbors are processed successfully, we mark the node as visited by setting its state to 2 and return true. This ensures that the node and all its paths have been validated, completing the depth-first search. Here, we start with an example where all paths lead to the destination without any cycles. The input specifies 4 nodes and edges connecting them as described. The source node is 0, and the destination is node 3. First, we construct the graph as an adjacency list. In this case, node 0 points to nodes 1 and 2, while nodes 1 and 2 both point to node 3. Next, we ensure that the destination node, which is node 3, has no outgoing edges. Since this condition is satisfied, we initialize a state array where all nodes are set to 0, indicating that they are unvisited. We then begin a depth-first search, DFS, starting from node 0. As we visit node 0, we update its state to 1, signaling that it is currently being explored. From node 0, we explore its neighbors, nodes 1 and 2. Starting with node 1, we visit it and mark its state as 1 to indicate ongoing exploration. Node 1 has a single neighbor, which is node 3. Proceeding with a DFS on node 3, we mark node 3 as visiting and note that it is the destination with no outgoing edges. Therefore, we return true for this path and mark node 3 as fully processed by updating its state to 2. Returning to node 1, since all its neighbors lead to the destination, we mark node 1 as fully visited by setting its state to 2. Next, we perform a DFS on node 2, the other neighbor of node 0. We mark node 2 as visiting by updating its state to 1. Node 2 also has a single neighbor, which is node 3. Since node 3 has already been fully processed, we can immediately return true for this path. After confirming that all paths from node 2 lead to the destination, we mark node 2 as fully visited by setting its state to 2. Finally, returning to node 0, we note that all of its neighbors, nodes 1 and 2, lead to the destination. This allows us to mark node 0 as fully visited by updating its state to 2. The final output for this example is true, as every path from the source to the destination is valid. In this example, there is a path that does not lead to the destination. The input specifies 4 nodes and edges connecting them, including a back edge from node 2 to node 1, creating a potential cycle. The source node is 0, and the destination is node 3. First, we construct the graph as an adjacency list. Node 0 points to nodes 1 and 2, node 1 points to node 3, and node 2 points back to node 1. We check that the destination node, node 3, has no outgoing edges, which is valid. We then initialize the state array with all nodes marked as unvisited. Starting a DFS from node 0, we mark it as visiting and explore its neighbors, nodes 1 and 2. Beginning with node 1, we mark it as visiting. Node 1 has a single neighbor, node 3, so we perform a DFS on node 3. When visiting node 3, we confirm that it is the destination node and has no outgoing edges, so we return true for this path. Returning to node 1, we mark it as fully visited since all its paths lead to the destination. Next, we perform a DFS on node 2, the other neighbor of node 0. We mark node 2 as visiting and explore its single neighbor, node 1. However, node 1 has already been fully visited, so we return true for this path as well. After confirming that all paths from node 2 lead to the destination, we mark node 2 as fully visited. At this point, all neighbors of node 0 seem to lead to the destination, so we attempt to mark node 0 as visited. However, the presence of a cycle between nodes 2 and 1 invalidates the result. Specifically, node 2 leads back to node 1, which can in turn revisit node 2, creating an infinite loop. This violates the condition that all paths should terminate at the destination. As a result, the algorithm returns false for this input, indicating that not all paths from the source lead to the destination. In summary, the algorithm uses a state tracking mechanism to ensure all paths from the source terminate at the destination without encountering cycles or invalid paths. By marking nodes as unvisited, visiting, or fully processed, the algorithm is able to detect cycles and confirm whether all leaf nodes align with the destination. This systematic approach ensures that the problem conditions are rigorously validated, leading to a correct determination of whether all paths from the source lead to the destination. To analyze the time complexity of this solution, we need to consider both the graph construction and the depth-first search traversal. First, constructing the graph involves iterating through the list of edges to populate the adjacency list, which takes time, where e is the number of edges. Next, the DFS traversal explores each node and its outgoing edges. Since each edge is visited at most once, the traversal also takes time. Additionally, for every node, we check its state, which is an O(1) operation per node. Combining these, the total time complexity of the solution is O(e), where e represents the total number of edges in the graph. Now, if we analyze the time complexity in terms of both nodes and edges, we can express it as n plus e, where n is the number of nodes and e is the number of edges. This is particularly relevant for sparse graphs, where e is often proportional to n, as e is at least n1 for a connected graph. Moving on to space complexity, the storage requirements include three components: the adjacency list for graph storage, the state array, and the recursive call stack during DFS. The adjacency list requires space to store the edges. The state array, which keeps track of the state of each node, consumes space since it has one entry per node. Finally, the call stack depth in the DFS can go up to in the worst case, such as when the graph is a linear chain or a tree. Adding these components together, the total space complexity of the solution is n plus e, accounting for graph storage, the state array, and the call stack. Now let's discuss the best, average, and worst case scenarios. In the best case, if the graph is small and the source node is disconnected or there are no valid paths to the destination, the DFS terminates early. Here, the time complexity is proportional to the nodes and edges explored before termination, which is n plus e. For the average case, in a well-connected graph, the algorithm typically explores all nodes and edges reachable from the source, resulting again in n plus e. In the worst-case scenario, such as a complete graph or a graph with many redundant paths, the DFS processes all nodes and edges. While the time complexity remains n plus e, the number of recursive calls and the constant factors may increase. Finally, let's compare this optimized approach with a brute force one. A naive method would involve enumerating all possible paths from the source to the destination using backtracking. This would result in exponential time complexity, k to the power of n, where k is the average number of neighbors per node. In contrast, the optimized approach avoids redundant computations by using a state array to track visited nodes, preventing cycles and reprocessing. This brings the time complexity down to n plus e. To understand why this is efficient, note that each node is visited at most once due to the state array, and each edge is traversed at most once during DFS. This ensures the algorithm processes nodes and edges linearly, even in the worst case. The space complexity is also linear due to the adjacency list, state array, and call stack. In summary, this solution achieves a time complexity of O, n plus e, and a space complexity of O, n plus e, making it highly efficient for solving this problem. In this section, we'll look at some common mistakes to watch out for when solving this problem. First, failing to handle cycles in the graph can lead to infinite loops or incorrect results. For example, if a path loops back to the source or another node in the current path, the algorithm may get stuck or produce invalid answers. To fix this, you can use a visited set to track nodes during the current path in a depth-first search, or employ a topological sort approach to eliminate cycles entirely. Another common error is assuming that all nodes are reachable from the source. In reality, some nodes might be disconnected, so it's crucial to perform a reachability check using DFS or BFS to ensure you're only working with relevant nodes. Finally, don't ignore the destination node's out degree. The destination node must have an out degree of 0, meaning it can't have outgoing edges. If it does, it violates the problem's requirements, so you should always validate that this condition is met before proceeding. Another pitfall is forgetting to handle dead-end nodes. A dead-end node is one with no outgoing edges, but if it's not the destination node, it can invalidate the solution by trapping paths before they reach the destination. To address this, you must ensure that every dead-end node is either the destination itself or part of a valid path. Additionally, edge cases in the graph representation can cause unexpected behavior if overlooked. Sparse graphs, self-loops, or multiple edges between nodes are examples of such edge cases. For instance, a self-loop at the destination node could violate the termination condition. Hence, it's important to validate the graph input and account for these scenarios during your DFS or BFS implementation. When preparing for interviews, there are several key insights to keep in mind. First, cycle detection is essential. Be ready to explain how your approach handles cycles, whether through recursion in a visited set or by using a topological sort. Next, the validation of the destination node is a critical condition. You should highlight how your solution ensures that the destination has no outgoing edges. Discussing edge cases is also important. Mention how you handle disconnected nodes, self-loops, and sparse graphs. Additionally, don't forget to analyze the time and space complexity of your solution. For example, a DFS-based approach typically has a time complexity of O, V plus E, where V is the number of nodes and E is the number of edges. Finally, talk about alternative approaches like DFS versus BFS and their trade-offs. DFS might be simpler for cycle detection, while BFS can be more intuitive for exploring the graph level by level. This problem is closely related to other problems you might encounter, and understanding these connections can deepen your understanding of graph algorithms. For instance, LeetCode 207, course schedule, involves detecting cycles in a directed graph, which is a similar challenge. LeetCode 210, course schedule 2, uses topological sorting to determine a valid order in a directed graph, another concept that can be applied here. LeetCode 802, find eventual safe states, focuses on identifying nodes that eventually lead to terminal nodes, which aligns with the idea of validating paths in this problem. Lastly, LeetCode 1129, shortest path with alternating colors, adds constraints to how the graph is explored, providing further practice with directed graph problems. Let's now explore some alternative approaches and their trade-offs. Using depth-first search with cycle detection is a common approach. Here, you use recursion along with a visited set to track nodes in the current path. This method is simple and intuitive but can encounter stack overflow issues if the graph has deep recursion. Another option is breadth-first search for level-wise verification. BFS uses a queue to explore the graph level by level, which avoids recursion depth issues. However, it requires extra bookkeeping to track the validity of each path. A third option is topological sort, where you pre-process the graph to identify cycles and validate its structure. This approach is efficient for acyclic graphs and ensures correctness, but it requires the graph to be a directed acyclic graph, or DAG, so you might need additional pre-processing to handle cycles. Finally, a less common but effective alternative is reverse graph analysis. In this approach, you reverse the graph and focus on the destination as the starting point. From there, you check whether all nodes can reach the destination using DFS or BFS. This simplifies the problem by flipping the perspective, but it does come with trade-offs. For instance, you may need additional memory to store the reversed graph, which could be a limitation in cases with large input sizes. This method can be particularly useful when the destination's connectivity is easier to analyze in a reversed structure. By knowing these approaches and their trade-offs, you can choose the best method based on the problem constraints and interview requirements. Thanks for sticking with us through this walkthrough of LeetCode problem number 1059. To summarize, we used graph traversal techniques like DFS and focused on cycle detection to validate all paths from the source node. The time complexity of our approach was O, V plus E, and we covered key concepts like detecting cycles and handling edge cases. If you enjoyed this explanation, be sure to like and subscribe for more problem-solving content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!